All right, in this video's lesson, we're going to be continuing our discussion about the idea of linear programming. We've seen kind of all of the parts necessary to solve a linear programming problem. So we've seen the graphing of the constraints, the using of the objective function. We've even seen how to set one up, but we've never actually been able to work through one all the way through. So today we're going to go ahead and work through two examples of linear programming. The first of which is going to be talking about a real world scenario where we're looking at a parking lot. So we've got a parking lot attendant who's trying to determine the number of cars and buses to allow into their parking lot. The area of the parking lot is 600 square meters, and a car requires 6 square meters, whereas a bus requires 30. The attendant can only handle 60 vehicles. And so if a car is going to be charged $250 and a bus is being charged $750, how many of each should be accepted in order to maximize the profits? Okay, so let's break this down first, deciding what our variables, constraints, and objective function are. So first off, our variables are kind of what we want to know our information about. In this case, we want to know how many of each type of vehicle we're going to allow into the lot. And so there are two different types of vehicles. There was cars and there were buses. So I'm going to let X be my cars. I'm going to let Y be my number of buses. Now, obviously, we like to try to use variables which kind of match the letters, at least in our two things we're trying to find. The problem with letting C be cars and B be buses is that when you go to graph it, which one is going to be on your x-axis and which one's going to be on your y-axis. So I would encourage you to go ahead and use x and y for your variables. Otherwise, it can get a little confusing. Now, as for our constraints, and in other words, what are we limited by? And there's a couple different things we're limited by. The first is we're limited by space. We only have 600 square meters. The next is we're actually limited by the number of vehicles. We can only accept 60 vehicles in total. So as far as our constraints, let's talk about the area constraint first. So when we're talking about area, we can say that a car is going to take up 6 square meters. So for each car, which is each X, that's going to take up 6. Whereas a bus is going to require 30 square meters. So 6X plus 30Y can be no more than 600 square meters. So it must be less than or equal to 600. Now, in order to make graphing a little bit easier in just a little bit, I would encourage you to simplify that. And since everything in that inequality is divisible by 6, to rewrite it as X plus 5Y is less than or equal to 100. As for our second inequality, so we've got the attendant can only handle 60 vehicles. That means that when you take X plus Y, you must be less than or equal to 60. Now again, I'm not going to be able to simplify that at all. Just going to have to leave that as X plus Y is less than or equal to 60. However, there are two more constraints, and these are ones that weren't really mentioned in the prompt, but are two that you're just going to have to remember, which is that you cannot have negative buses and you cannot have negative cars. So both X and Y must be greater than or equal to 0. All right. Finally, before we start to graph, let's go ahead and set up our objective function. So what we're trying to maximize or minimize. In this case, obviously, we're trying to maximize profit. So let's call our objective function P. And then to calculate our profits later on, a car is going to be charged $250, so that would be 2.5 for each X, whereas a bus is going to be charged $750, so 7.5 for each Y. All right, so now we've got all that information. Let's go ahead and go to graphing. Now, we've got some pretty big numbers to graph, like 160. So let's do this. Rather than trying to count by ones, which would make this graph really hard to do, let's go ahead and just count by tens. So what that'll mean is we'll go from 0 to 10 to 20 to 30 and so on, 40, 50, this would be 60, 70, 80, 90, all the way up to 100. Then we'll do the same thing for our y variable. So here would be 10, 20, 30, up to 60. And once again, y will go up to 100. All right, so as far as graphing these inequalities go, let's start with this inequality right here. And I'm going to go ahead and graph these by hand. If you want to use a graphing calculator like Desmos, obviously you can. But they're in standard form, which does make them a little bit easier to graph. So we would take x, set that equal to 100, and then there's going to be your x-intercept for this inequality. Then we'll do the same thing with 5y, so we'll set 5y equal to 100, and to solve for y, divide each side by 5, so y is going to be equal to 20. So then your first inequality is going to look something kind of like this. And as for shading, we're less than or equal to in that equation, so we're going to shade everything below that line. Now again, remember, x and y have to be greater than or equal to 0, so that's why I'm only shading in the part that's in the first quadrant there. All right, let's go and graph our second inequality. So x plus y less than or equal to 60. In both cases, setting x and y equal to 60, no solving is necessary. You can just go straight to putting those points on your graph. So then here is the second line that we're going to be using. And again, as far as shading goes, we were less than or equal to 60, so we're going to shade in everything below that line. So now looking for our feasible region, there was one region that we shaded in twice, which was this piece of our graph right in here. And so we're going to have 4 different vertices to check to see what our solution should be. The first is at 0, 0. The next is at 0, 20. You also have a point out here at 60, 0. And lastly, a point right here, which is at 50, 10. So let's use those vertices as well as our objective function to set up our table. So remember, when you're setting up your table, your points x, y are going to go in your first column. Your objective function itself, so the expression, is going to go in the second. And in the third column, that's going to be your total profit, so that's going to be P. All right, so taking a look at those points, let's go ahead and fill those into our first column here. And then we can go ahead and start substituting those into our equation. So obviously when you put in 0, you're probably not going to end up maximizing your objective function because the profit there is going to be 0. When you put in 0, 20, we're going to end up with a total profit of 150. So far that's our best. Next, when you put in 60, you're going to also end up with 150. So far we've kind of got 2 different options as far as maximums go. So let's check our last option. So take 2.5 multiplied by 50 plus 7.5 multiplied by 10, which 2.5 multiplied by 50 would be 125. 7.5 multiplied by 10 would be 75. So your total profit would end up being 200. All right, so looking for our maximum, that's going to end up being the last point that we checked. So that would be that we want to allow, or we should allow, 50 of our x variables, so 50 cars, and 10 of our y variables, so 10 buses, for a maximum profit of $200. So that's going to be the part that's going to be easy to forget, is that when you're answering these questions, your final answer needs to be in the context of the problem that you're working in. It's not enough to just circle a point, say here's the answer. Really doesn't answer the problem. You've just circled a point and a number. So make sure when you give your final answer that you're doing so in context. All right, let's take a look at one more example, and then hopefully that'll be enough to get you the idea of what's going on here. So we've got Yum's Bakery now, which is going to bake two types of bread, wheat and honey oat. They're almost out of oats and flour and want to optimize their profits with the remaining supplies before they reorder. So they have 60 pounds of oats, 16 pounds of flour remaining. And so 1 pound of wheat bread uses 3 pounds of oats. One batch of honey oat uses 6 pounds. Whereas one batch of wheat bread uses 1 pound of flour, and one batch of honey oat also uses 1 pound of flour. Let's find out how many batches of each the bakery should make in order to maximize profits. If each batch of the wheat bread sells for $35 and each batch of the honey oat sells for $55. All right, so first off, we want to know what the variables are. Again, that's where you want to look for how many of each. In this case, how many batches of each bread. That tells you what your two variables are going to be. And so in this case, our two types of bread were wheat and honey oat. I'm going to let X be wheat, and I'm going to let Y be the honey oat. All right, as far as limitations go, they have 60 pounds of oats, 16 pounds of flour. Those are the two things that we're limited by. So let's first talk about the 60 pounds of oats. So it tells us that one batch of wheat bread uses 3 pounds of oats, so that would be 3x. And one batch of honey oat bread uses 6 pounds of oats, so that would be 6y. And so that's going to need to be less than or equal to our number of oats, which was 60. As for the flour, it tells us that there were kind of 1 pound of flour for each type of bread. So that would be that 1x plus 1y needs to be less than or equal to 16. All right. Lastly here, we do have 2 more constraints. Don't forget that you cannot have any negative constraints or any negative batches of wheat and honey oat. So you've got to make sure that both of those are at least 0. Lastly, for our objective function, once again, we're trying to maximize profits, which is a pretty common objective function to have. Wheat is going to sell for 35, so that's 35x. Honey oat is going to sell for 55, so that's 55y. All right, so as we get ready to graph, let's first go ahead and simplify that first inequality. So let's go ahead and divide everything by 3 to make it a little easier to graph by hand. So that would be that x plus 2y must be less than or equal to 20. And then as far as our graph goes, I'm not quite sure that we're going to have enough to go out all the way up to 20. So let's do this. Let's just go ahead and count by 2s. So that would be 2, 4, 6, 8. Here would be 10, 12, 20, or it's 14. Let me go ahead and get that fixed. Then we would have 16, 18, all the way up to 20. And then here would be 22, and then 24 would be kind of the one off to the side. And then we'll do the same thing for our y variable. So we'll again count by 2s. So here would be 2, 6, 10, 14, 18, 22, 26. Here would be 30. And here would be 34. So actually, I think I got off on the x-axis. Let me go back and fix that here. There we go. Cool. So graphing these, let's start with our first inequality. So let's start with the x plus 2y less than or equal to 20. Finding our x-intercept, we'll set x equal to 0. And so x is equal to 20. So that would be this point right here. Next, we'll go ahead and do the same with our y variable. So 2y equals 20. And then to solve for y, divide each side by 2. And we'll get that y is equal to 10. And so then drawing in your line through those points, here that is for us. And then don't forget your shading. You were less than or equal to, which again, pretty common with these linear programming problems for everything to kind of be less than or equal to, since they are limitations or constraints. So a lot of shading kind of under the feasible region is what you're looking for. All right, as for the second inequality, notice the x and y are just kind of by themselves. So when you set those equal, that'll be pretty easy. Both x and y should be equal to 16. So we'll go ahead and put those points down. And then graph will look something kind of like this. Okay. So looking at the points on our feasible region, I guess we should shade for that first, make sure that's everything below. But the feasible region ends up being very similar to what it was on the first problem. It's kind of this region in the bottom left corner of our graph. So again, we should have 4 vertices to check to see how well our profits are going to be able to do. All right. And so checking each of those, the first is at 0, 0. The next is our y-intercept at 0, 10. The next is our x-intercept at 16, 0. And the last, be careful with the labels, is your point at 12, 4. All right, so let's go ahead and get our table set up with those points as well as our objective function. So points again on the left column. And then we'll fill in our objective function in the center. And then the last column will be for our profits. Again, not surprisingly, when you put in 0, 0, you're going to end up with a profit of 0. Which, unless you're trying to minimize profits, which wouldn't make much sense, probably not going to use that as our choice. All right, next we'll plug in 0, 10. That leaves us with a profit of $550. So far, that's going to be our maximum. Next, we'll plug in 16, 0. So that would just be taking 35 multiplied by 16. So your total profit there is going to be 560. So now just a little bit more, but there's our max profit so far. Lastly, we'll plug in 12, 4. And so then your max profits for that would end up being 640. So it looks like that's going to end up being our maximum. All right. So we should produce, here's our final answer. We want 12 of X, so 12 batches of wheat. And 4 Y, so 4 batches of honey oat. And that's going to be for a maximum profit of $640. All right, I hope that was helpful. Again, that's kind of our wrap up of linear programming. That officially puts us kind of at the midway point of Unit 2. Once we're done with our project, we will come back and continue to learn a little bit about linear systems by studying what are called matrices. Until then, have a good rest of your day.